Number 7, when do we know enough about relationships between diversity and resilience to integrate these principles into practical conservation action and planning? Or do we? I'm sorry, do we know? And I say yes. People may argue with me about that, but I say yes, unless the rules change. And again, this gets back to question 1. However, given the acceptance of uncertainty in ecosystem management, even the potential for fundamental shifts in ecosystem response to the disturbance should not hinder conservation action and planning. So what I mean by that is that I think we know enough about how ecosystems function to begin to use the practice of conservation planning and action. And even if we don't, we shouldn't let that stop us from doing it, because unknowns cannot be always defined by definition or planned for. And 2, not all unknowns are bad. There may be some things we're not looking at or planning for, which actually turns out to be good. So question 8, last question. What's been the major challenges and opportunities for integrating ecosystem-based management and land use planning into climate change adaptation planning? So here's what I believe are the challenges, and I think there's 3 of them. The first challenge is the need to start to use the knowledge proactively, not reactively, despite uncertainty. So getting back to that first question, let's not look at these things after the damage is done. Let's look at it before. Second, we need to better communicate knowledge to land managers. As scientists, we can find some wonderful things, some wonderful relationships, some wonderful tools, but unless we can communicate that to a land manager, they do no good. Third, the major challenge is increasing the risk of unknown unknowns, where pre-existing knowledge no longer helps understand or react to a developing disaster. We need to find a way to better look for these things. Otherwise, these are going to be the kinds of situations, these unknown unknowns, which are going to be by far the greatest impact in the future. So, my last slide here, or last 2 slides are, we have some web-based tools that we're beginning to develop to address these major challenges for proactive ecosystem planning and improved communication between scientists and land managers. And I'm going to pull one up called TACAMO. And I happen to like TACAMO because I'm a principal investigator on it. But basically what TACAMO is a template for assessing climate change impacts and management options. It's a web-based tool. It uses scientific information into a web-based tool that allows you to look at your specific location, see what kind of management or stress implications there are for that particular location, and then cross-reference that with management options to address those implications. So it allows you to proactively say, what could be the negative impacts in the future, and what can I do about it beforehand? And so this is being developed with the Forest Service research and with National Forest System. Good thing I'm ending. So the summary take-home points. Historically, most ecosystems have been reactive and not proactive. This is the most costly, least effective approach to ecosystem sustainability. Scientific knowledge exists to support more proactive ecosystem planning, but expect these unknown unknowns. So expect big surprises along the way. The new unknowns are potential to be more problematic than the uncertainties associated with known problems. And new web-based tools are coming online that will help us as scientists to assist land managers to be more proactive in our addressing of these issues, and we need to be open to working with land managers in the future to make this happen. So if you want a copy of the presentation or learn more about TACAMO, you can contact me at this address. I'm at NC State, and I'd like to thank the Forest Service International Programs Office and USAID for providing funding for this support. Thank you.
Thanks, Steve. I think in the interest of time, I'm just going to start with the next presentation, but you have been handed a few post-it notes, so if you have questions, please write them down. And Erica can actually stand up. Erica will be collecting them, and if you need more, let Erica know. Our next speaker is Dr. Mark Stolton. He's a senior marine scientist at the Nature Conservancy. Mark has been working, he's also based at the University of Cambridge in the UK. He worked extensively on global assessment of marine coastal biodiversity and lately has been involved in the Global Atlas for Mangrove and a global review on the role of mangroves in reducing risk of coastal hazards. Mark, up to you.
Thanks, Imen. I think this is quite a nice follow-on from that talk because I'm going to get a little bit deeper into some science and really maybe dealing with how much we actually know about some of the unknowns. Very broadly. How do I change slides? There we go. So the issue, as we all know, I'm going to focus very much on the coastal environments and focus in on mangroves. The coastal population densities are 5 times that of the averages around the planet. And here you can see the east coast of China, and very, very dense populations. And of course, this is part of the thing that gets us worried. This was last week, and you can see Jeju was a bunch of somewhere. There we go. That's where we are. So 2 typhoons were just here last week. The threat facing these coastal societies is large, but people are moving into coastal areas, so becoming more and more vulnerable with the added potential threat of increasing amounts of extreme events and sea level rise, kind of sandwiching on top of that increasing vulnerability. So I'm going to talk about the role of nature in helping to defend coasts and coastal populations. And to some of us, it seems blindingly obvious when we look at nature. You know, this is a photograph in the Indian Ocean, and you can see how the coral reefs are just there, a barrier to the waves that are quite strong at timber creeks. This is in the southern US, where you've got this very dense barrier of dense marshes and almost like a wall of rock, the oyster reefs there. Mangroves too, seeming to break waves. It seems to be, to many of us, almost a non-brainer. But in fact, there seem to be 2 sort of realities out there. On the one hand, we've got the NGOs, this is the World Bank as well, telling us natural ecosystems can help, can reduce vulnerability and so on. On the other hand, this is probably the most heavily used of the manuals being used by engineers, coastal engineers, has nothing about the role of ecosystems in protecting coastlines, and that's thousands of pages long, and that is the go-to Bible for coastal engineers and planners. So we need to try and bring those together. And to my mind, it does seem that one of the challenges is there's a lack of hard science. A lot of the stories we're hearing about are anecdotal. We hear about how many people survived in villages behind mangroves compared to people who were killed in villages who lost their mangroves, and so on. Sometimes we've got traditional knowledge, but the coastal planners and engineers, the ones who are making major decisions now, they need rules, they need models, they need numbers in order to make the case of using nature. My own organisation, the Nature Conservancy, works on multiple levels, and this is just a background as to how we got into this. We have people in the field who are involved in habitat protection, also increasingly in habitat restoration. We also have been building a lot of tools to help us make decisions. Firstly, it was in conservation prioritization, where we were going to invest our efforts to protect nature. But that's kind of morphed quite nicely into some of these decision support tools, where we're looking at the role of nature in protecting people. We're engaged increasingly at the international policy level. And I guess from those multiple levels, we've decided to focus quite heavily on the role of nature in protecting people. And that's, we formed a small coastal resilience program within TNC. And within that program, there's a group of us who are trying very hard to make the case for, well, to improve the scientific base for making these decisions. 2 years ago, almost exactly, we hosted a workshop in the US with quite a few policy people, as well as scientists and engineers, to really ask the question, well, what's missing from the agenda? Why aren't people taking up the use of nature more in coastal protection? And we came up with a series of recommendations, but right at the top was the need for better science, more numbers, in order to inform active uptake of nature. We needed also better economic arguments to be made, and those arguments wouldn't just be about how much money do you save on coastal engineering, but what are the benefits, the additional benefits of keeping nature? Those might be fisheries benefits, there might be tourism benefits, but all those need to be added into the equation. And it's complicated, and I think that's an important point. So with a postdoc working with me in Cambridge, we've begun to start a more systematic appraisal of how nature works. You can look at this from multiple angles. What are the threads? What are the processes going through those threads? And what are the processes of reducing the risk? It's not just one process, there's wave attenuation through processes such as shoaling and drag, there's the elevation change, and so on. I'm going to walk you through some of this in the next few slides. And these processes are acting through many different ecosystems, sometimes multiple ecosystems combined. We're not working alone. We've hosted a number of workshops now, fairly academic workshops, trying to get the experts in coastal geomorphology and ecosystem science together to help and advise us. As you can see, we've got a growing number of partners, and so it's very much a sort of team effort. So I want to focus quickly then on mangroves, which is where we've begun our journey into this work. And a good way of understanding the way we're thinking about this is that we're looking first off for what evidence is there that there is a service provided by the ecosystem in terms of coastal protection. And what is it that are affecting the level of that service? What is it that makes one mangrove good at protecting a coastline versus another which may be less good? How does it vary? And if possible, to quantify those relationships, what do you need from that system? Have people been built some of this knowledge yet into models that can be used? And is anyone using those models in coastal management? So I'm just going to start off. So I've already told you I'm focusing on mangroves. This is just about one role that mangroves perform. That's the role of attenuating wind waves. So these are the waves you see on the beach on a daily basis. This is not storm surges or hurricanes at this point. And it turns out, through this fairly extensive review of hundreds of papers, there's quite a few papers that have shown, all of them have shown, in fact, that waves can be attenuated by mangroves, which is not surprising, but we need the numbers, as I said. And some of them are producing the numbers, and we can see the process of attenuation of the wave as it goes through the mangrove. This is 100 meters of mangrove here. The waves are getting smaller. And from a variety of studies, we can start to quantify that. And we're starting to pick out what it is that makes a mangrove forest better or less good at attenuating waves. And it's fairly obvious. It's how wide is the strip of mangroves you've got for the wave to travel through, but it's also affected by the structure of the mangroves. They've got big aerial roots or no aerial roots, low branches, the depth of water, which of course varies through this tidal cycle, and the topography and the slope of the land. If we can start to characterize some of those issues, we can start to give this information to people who really need it. And people are beginning to use this already in models. So I'm not going to go through this, but there are 3 models that we're aware of that have actually built mangroves into the model. And in this example, they use a model to estimate how much a mangrove island in front of a port in India was helping to attenuate waves. And they also started to model, if we were to extend through restoration this island, would we provide additional protection to the port? And of course they would. So this is pretty exciting when we're starting to see things like that already being used. We see it as urgent that we start getting this information out. So although we're a bunch of academics, we're actually putting this stuff out even prior to peer review. This report's just come out in the last few weeks. It's available online, and we hope to also peer review it and get some other articles out of it, but we recognize it's critical that we start communicating this information as soon as we can. As I said, this is just part of the role that mangroves can play, and just quickly to think of a couple of other services. So storm surges, which are a real issue in many, perhaps most mangrove areas, are when the entire surface of the sea rises up through the role of wind blowing across the seawater surface. And this is a model just come out which shows the role of mangroves in holding back that surge of water, that storm surge. So here you can see very high elevation water, but being held back from this strip here by the mangroves. If you hypothetically remove the mangroves in the model, you can see that the water doesn't get as high here, but it goes way further inland, a much greater threat to people and resources. So mangroves do have a role in storm surge reduction. So this is kind of a large spatial scale, if you like, thinking of a large temporal scale, this gets a bit complicated. As sea levels rise, there's some evidence that quite a few coastal ecosystems can keep up with sea level rise by the organic growth, whether it's the coral reef, the seagrass, the salt marsh, the mangroves can keep up with sea level rise, and therefore almost act as a living barrier that keeps up and helps to maintain that defense. But it's a complex process, and again, the simplistic, oh, well, mangroves can keep up is actually wrong. They can in some places, and we need to understand what's going on, and there are multiple processes. I'm just going to do this quickly because I think we're pushed for time. But you can start to see that we need to build these sorts of models in order to understand really what is going to go on and what's going to go on in any particular place before we can start recommending mangroves are the solution. They may be in some cases. But here's this process that I was trying to describe, how this is, if you like, this is sea level rise, the blue line, through time. If we're talking about sea level rise, this is what your traditional engineered coastal defense would do. You'd build a wall that would cope. Then you have to build a higher wall, and then you have to build a higher wall. Well, the idea with mangroves, with this fast, high productivity, rapid growth, a lot of it just going straight into the sediments, the mangroves will keep up. And even if you have a major storm, which causes a loss in elevation, they should be able to catch up and keep up again. So if we can show this and know this, in many ways they're going to be better than engineered defenses. I'll skip over this except to say that, as you can see, we've done quite a good job of identifying in bold here the sorts of information we need for wind and swell waves. These grayed out areas tell us that we actually think that information doesn't exist at all for many of these other ecosystem services. So I want to think a little bit about how we can start to put some of this knowledge into action. This is a couple of slides I got from Ty Wamsley of the US Army Corps of Engineers, where they're starting to use models to look at, this is the Mississippi Delta here, so New Orleans is up here, I think. And it modeled a storm surge, and it's a very large salt marsh. The salt marsh is all around here anyway. What they've done essentially is model, if we were to restore large areas of salt marshes, what would happen to the storm surge? And you can see in this model it's much reduced at this area. So as you can start to build these models, I think they're going to have a very powerful influence. And it's great that the US Army Corps are already starting to think like that. This is our own work. We're doing a lot of ecosystem restoration, particularly on oyster reefs. And as we start to know what factors are that will help to reduce coastal erosion, this is the Federal Bay in Alabama, we're developing these dashboards which enable managers to say, well, okay, here's my setting, you can change these various elements of the dashboard, and you can come up with a map that advises you where you're most useful, you've got most sort of results for your investment in some of these areas where you've got a lot of wind wave energy coming in, rapid erosion, and you can do these sorts of things, which are oyster reef restoration, and you'll be able to reduce coastal erosion. It is a really complex picture. I started to pull this together just to try and think, in a sense, another group that needs to start using this information is the reinsurance industry. They need to understand, in a simplistic way, I suppose, where to say we can rely on mangroves or coral reefs or whatever. And here you start to see how we now need to think about these things. We can't just think mangroves do this. We need to think about what are the stressors. Are we talking about wind waves, or is it a place where you might expect major storms? Are we concerned about tsunamis? What's the potential future sea level rise? And then what are these settings for these systems? Are they deltaic mangroves? Are they nicely embayed and therefore secure? What are the timing settings? It's a complex picture, but we think we can get towards that. And we mustn't think of any of these uses in isolation. We have to think of coastal defense as a many-tiered process, which starts with human behavior, starts with issues such as legislation and zoning, discouraging new building of places at sea level, setbacks from the coast, then there may well be a place for bringing engineering together with natural systems to try and protect coasts. Which gets me briefly to my last topic, which is the idea that we don't necessarily need to think of nature acting on its own. And there's a lot of talk now about hybrid approaches, or grey plus green engineering. From small scale, this is the shorelines work in Virginia and the US on the East Coast, where individual landowners are being encouraged to, rather than just build ramparts to protect their coastlines, they're actually building these slightly offshore levees and then planting seagrass plants to try and both enhance their view, but actually also to maintain their coastal protection. Through to this, which is a newly built sand island off the coast of Holland. They have been doing beach nourishment along this coast for a long time to try and protect their coast. Every year putting millions of tons of new sand onto the beaches, which is getting eaten away. And of course that process, although it's semi-natural I suppose, is still quite damaging. They came up with this idea of building a huge sand island. I think the scale is kilometers in length. And so this is all new sand just being